Bismillahirrahmanirrahim. We will start with quote of the day, which is wealth and children are but adornment of the worldly life, but the enduring good deeds are better to your Lord for reward and better for one's hope. I am Dr. Temia Ayub, and today I will be presenting the topic of bias, confounding, and interaction under the kind supervision of Professor Dr. Saira Afzal, Dean, Institute of Public Health, Lahore. These are the learning objectives of today's class. First, we will distinguish between internal and external validity and then define and classify major types of bias and why they are important. Then, explain confounding, differentiate confounding from effect modification or interaction, interpret additive and multiplicative interaction with real examples, and then in the end, I will shortly describe what is DAG, and then we will do multiple choice questions. So this is the validity framework. Sorry. And then in this, we have two important concepts, internal validity and external validity. In internal validity, it is, are the study's result valid for the study population? And selection bias, information bias, and confounding are important for internal validity. And the threats to internal validity are mainly bias and confounding, as explained. Then we have the concept of external validity. Can findings be generalized beyond the study population? Effect modification across strata, sampling and eligibility restrictions, healthy worker or volunteer effect. It requires effect modification analysis. So this is another diagram to shortly explain the internal and external validity. So internal validity tells us about the truth in the study, but the external validity is more about generalization and about the truth in the real life. Again, internal validity relates to how well a study is conducted, whereas external validity relates to how well the findings are, how applicable the findings are in the real world. Now we come to the concept of bias. What is bias? Bias is any systematic error in the design, conduct, or analysis of a study that results in a mistaken estimate of an exposure effect on disease risk. So it can be systematic. Unlike random error, bias does not cancel out with larger samples. It can be it can be directional, can bias towards or away from null, both equally problematic if they are moving towards null or away from null. It can be preventable, best addressed at study design stage, hard to fix post hoc, and classifiable. Three major families: selection, information bias, and then there is the confounding. Okay, so this is a diagram showing us types of bias. So bias has mainly two main types: information bias and selection bias. All these types of the rest of the types of bias are classified in these two categories. So for information bias, we have observational bias, recall bias, or classification bias. And then for selection bias, it can be identification bias, non-response rate, etc. First, we come to selection bias. It occurs when participants differ systematically from non-participants, distorting the association between exposure and outcome. So we have healthy worker effect. Occupational studies, workers are healthier than general population. Control group inflated with ill non-workers. Then we have Bergson or Bergsonian bias, which is basically on hospital-based case control. Hospital patients differ from community cases. Hospitalization risk varies by exposure. Then we have non-response bias in surveys and cohorts. Those who respond differ from non-responders on key exposure or outcome variable. Loss to follow-up in longitudinal studies. Dropout correlated with both exposure and outcome leads to differential in attrition. Self-selection bias, cross-sectional studies and surveys. Volunteers differ systematically. Screening programs attract health-conscious individual. It is also known as volunteer bias. Again, this is a diagram showing what is selection bias. So there are different types. We have just discussed volunteer bias. Then there is another type, which is the survivorship bias. Successful observation or people are more likely to be represented in the sample, like those who are surviving a longer study. Then there is attrition bias, which is the follow-up of the bias, following up of the bias as explained. Sampling bias is there. These are some of the examples. Now we come to the information bias or measurement bias. It arises from systematic error. It arises from systematic errors in how data on exposure, outcome, or covariates are collected, recorded, or classified. For this, we have the first of all recall bias. Cases remembers past exposures more vividly than controls. For example, mothers of children with birth defects recall medications more thoroughly. Then we have observer bias. Investigator measures or record differently depending on group status. Clinician probes harder for exposure in cases than controls. Then we have interviewer bias. Interviewer behavior changes based on known case or control cases. Unblinded interviewer asks leading questions to cases. Then we have Hawthorne effect. Participants modify behavior because they know they are being observed. For example, dietary intake improves when participants know that it is being recorded. Now we come to the concept of misclassification, in which there is a comparison between differential versus non-differential. For non-differential, misclassification rate is equal across exposure groups. Independent of exposure or outcome status, it is generally biases towards the null. It underestimates the effect. It can increase or decrease effect in multi-category exposures. For example, laboratory assay with fixed error rates for all samples. Then we have differential bias. Differential misclassification, in which misclassification rates differs between exposure groups. It depends on case control or exposed or unexposed status. Can bias in either direction. It is very unpredictable. It is more serious, cannot assume direction of the bias. For example, recall bias in case control studies. This is another figure showing the differential and non-differential misclassification. So non-differential misclassification always leads us towards the null answer, that there is no difference between the two groups. Whereas the differential misclassification can go towards null or can move away from the null. So we do not know, it is very unpredictable as compared to non-differential. So potential impact again is of non-differential that biases towards the null, whereas differential bias can be in either direction as explained. So strategies to minimize bias, we have design, data collection and analysis. In design, we have randomized allocation, blind participants and investigators, also known as double blinding, then standardized exposure measurement and use objective outcome definition. For data collection, it includes train interviewers and blind them to case status, use validated structured instruments, maximize follow-up and track dropouts, blind outcome assessors to exposure status. And then we finally have analysis, in which sensitivity analysis for misclassification, sorry, quantitative bias analysis, and e-value calculation for unmeasured confounding, and similarly report loss to follow-up and concerned flow diagram should be followed. Now we come to a very important concept of confounding. So basically, many years ago, they did a study in which the exposure was cancer, and they find out that the people who were drinking coffee were more likely to have cancer. But later on, it was found out that basically those who were drinking coffee were more likely to smoke also. And basically, it was smoking which was leading to the lung cancer instead of the coffee. So, smoking here is the confounder, which is having a relationship between directly with the exposure, which is cancer. Outcome, which is cancer, and exposure, which is the coffee. So, confounding occurs when a third variable distorts the apparent association between an exposure and outcome, leading to an incorrect estimate of the true effect. So, it is associated with exposure. The confounder is unevenly distributed between exposed and unexposed group. Then there is independent risk factor for outcome. The confounder causes or predicts the outcome independently of exposure also. And it is not on the causal pathway. It must not be an intermediate step between the exposure and outcome. That is, it is not a mediator. So this is explained again because this is a very, very famous example of actual real life study. So the classic example was that coffee drinking leads to lung cancer, but it was not actually the true causal link. It was basically coffee drinking um, was more present in those who were smoking, and it was actually smoking which was leading to the lung cancer. So, the data can show that the crude or uningested in ratio risk ratio is 2.1, and it is positively associated with p-value significant. So coffee and lung cancer risk ratio can come out to be 2.1 with significant p-value. And interpretation is that it appears harmful. But when we adjust it for smoking in the statistical analysis, the risk ratio comes out to be 1.02, which is not true association. And the p-value is also not significant. So key characteristics of confounding variable. It correlates with the independent variable. It associates with the dependent variable. It introduces noise into the relationship, and it lacks relation to the research question. So it is a key characteristic of confounding variables. So this is again a diagram showing confounding versus selection bias. For example, studying the effect of alcohol on cancer. There is the whole population, and all alcoholics are in the population. And in this, 25% are non-smokers and alcoholic, and the rest are 75%, which are smokers and alcoholic both. So if the sample is taken from the confounding, it depends from where the sample is taken. The sample still represents the population, and in selection bias, the sample does not represent the population. No causal but real life association between alcohol and cancer in this kind of um, sample selection, whereas error in the estimation of association between alcohol and cancer. So, selection of right sample or representative sample is very important also. Controlling confounding. Design stage. It can be controlled by randomization. Distributes known and unknown confounder equally across groups, which is the gold standard. It controls all confounders simultaneously, and it is only applicable in experimental designs. Then we have restriction. Limit study to participants who share same level of potential confounder. Simple to implement, eliminates confounding within restricted range, and reduces generalizability, and cannot study restricted variable. And then we have matching, select control who match cases on confounder variable, individual or frequency matching. It is efficient, it ensures balance in small studies, and it cannot study matched variable. Matched variable must be analyzed accordingly. Then we have stratified sampling, ensure equal representation of confounder strata in exposed or unexposed group. It builds balance into sample before data collection. It requires prior knowledge of important confounder. And okay, these are the changes which can be done for controlling confounding at design stage. Then this is now coming off at analysis stage. For this, we have stratified analysis, which is the classic pathway. Then we have multivariable regression. It is the standard technique to do. It includes confounder as covariates in logistic, Cox, or linear regression model. It is most widely used. Then there are other methods like propensity score methods, inverse probability, weightage, and instrumental variable. So these are usually advanced type of statistical analysis, but multivariable regression is the common one. Then there is a concept of residual confounding. Confounding that persists even after adjustment due to imperfect measurement, unmeasured confounder, or insufficient categorization of measured confounder. So unmeasured confounder are those variables that are not collected in the study. For example, if we are collecting information about socioeconomic factors, there can be many socioeconomic factors, not just the only the salary of the individual. Then there are diet, stress in observational data, etc. Course categorization, grouping continuous confounder, for example, age in 10 years band leaves within group variation uncontrolled. Then we have measurement error in confounder. If the confounder is measured with error, adjustment is incomplete. It is classic attenuation applies. So then we come to the concept of effect modification. Effect modification occurs when the magnitude of an exposure effect on an outcome differs across strata of a third variable, which is the effect modifier. This is a real biological phenomena, not a problem to fix. We just have to be aware that this is happening. For example, in cases of aspirin and myocardial infarction, if we are computing risk ratio of aspirin and myocardial reduction in males and in females. So in males, the risk ratio comes out to be 0.68, which means that there is significant benefits. In female, the risk ratio comes out to be 0.97, as it is very near to 1, so there is no significant benefit. So sex is an effect modifier. The protective effects differ between males and females. So the key features for the effect modification includes association varies across strata of the third variable. So this is first variable, this is second variable, and this is third variable, and these are two strata of the third variable. Both stratum specific estimates reported separately. Effect modifier is a descriptor, not a confounder. It must be pre-specified in analysis plan. It is relevant for targeted intervention, precisions in public health. Additive versus multiplicative interaction. So additive interaction is that joint effect is not equal to sum of individual effects. It is measured through RERIAPSI. For example, in groups, unexposed or no modifier risk is 2%, and observed is also 2%. In exposed only, the risk is 6%, and observed is 6% also. But in modifier only, the risk is 3%, and observed it is also 3%. But in both, the risk comes out to be 7%, and which is more than adding. So RERI is more than 0, is positive additive interaction, and then we have multiplicative interaction. Joint effect is not equal to product of individual effects. For example, in Meyer ratio of RRs, interaction terms, again we have groups, and then we have outcomes. So in exposed with no modifier, same is 1 1, and in exposed only we have 3 3, and in modifier only we have 2 2. But if we do it for both, it comes out to be 12.0, which is um, which is basically calculated by multiplication of the upper two outcomes instead of just adding of the effect. Confounding versus effect modification. So confounding in nature, there is bias, which should be controlled, and effect modification is a biological reality which should be described. Then we have stratum specific estimates, similar across strata, homogeneous. There will be homogeneous, for example, but for effect modification, they will be different across strata, heterogeneous, like we saw for the sex in males versus females. And what to report? Confounding should be adjusted or pooled estimate should be reported. And in effect modification, stratum specific estimates should be given. Statistical test for confounding is it is not routinely tested, but for test for interaction or p-interaction is done for effect modification. Causal role of third variable, it distorts effect to outcome association. And in cases of effect modification, it modifies the strength of effect to outcome association. Goal of analysis is to eliminate it in case of confounding by adjusting it or controlling it. And for effect modification, it's to report it and describe it. So then we come to another important concept, which is the directed acyclic graph, or also known as DAGs. These are geographical graphical tools that encode causal assumptions about relationship between variable, helping identify what to adjust for and what not to adjust. So in cases of confounder, causes both exposure and outcome, it must be adjusted for. In cases of collider, it is caused by both exposure and outcome. Do not adjust for them. And then we have mediator on causal pathway of exposure to outcome, adjusting blocks causal effect. And then there is instrument, it affects exposure but not outcome except through exposure, and it is useful for analysis. So the concept I just wanted to give, some of these terms are specific to DAG diagrams and they are a bit difficult and new for first time. So I just wanted you to have a look at the diagram. So next time you are going to maybe they can be present in any thesis or they can be there in any research article. So you are just aware of them and know a bit about them. Okay. So just have a look at them, this diagram quickly. It is basically showing, it is a directed acyclic graph for alcohol use disorder. Minimal sufficient adjustment sets for estimating the total effect of alcohol use disorder on complications or death. So age, sex, race, and smoking. Uh, then AIS is abbreviated injury scale and ISS is injury severity score. So as you see, age, sex, race, smoking, all these are basically exposure which are leading to alcohol use disorder. And then all these are also affecting these factors, which again leads to the alcohol use disorder. And alcohol use disorder leads back to uh, number of rib fractures or accident and some stuff like that. So basically this is kind of more realistic application of how exposures and outcomes and confounders, they are actually related in real life instead of simple 2 by 2 table. DAG tries to give us a more realistic pictures of how things are working in relation with each other instead of separately from each other. So I just wanted to give the concept of this diagram type, which is DAG. So let's just go through it quickly. How to detect confounding in practice. There is a rule of 10%. If the crude and adjusted estimates differ by more than 10%, confounding is likely and the adjusted estimate should be reported. Then first, we should compute crude or unadjusted measure of association. They can be odds ratio, relative risk, etc. Then check if third variables meets criteria for confounding and it is associated with exposure and independent risk factor for outcome and not a mediator. Then compute adjusted or stratum specific or model adjusted estimate. This is done through sorry, regression or during using software for analysis. Then compare crude versus adjusted estimates. If the difference is more than 10%, confounding is present and then report should adjusted estimate should be reported. So this is these are the key takeaways. Now we come to multiple choice questions. A case control study examining pesticide exposure and Parkinson's disease recruits control from hospitalized orthopedic patients. Um, Later, researchers realized that orthopedic admissions were associated with occupational pesticides exposure. Which type of bias is most likely affecting the study? Recall bias, Bergson's bias, Hawthorne effect, observer bias, or non-differential misclassification?
A,
D.
Uh, Let me just quickly open the key or just check it like this. One second.
Either B or D.
Yes, B is the answer because it is based in hospital type of study. So it is the Bergson bias. In a cohort study investigating obesity and cardiovascular disease, participants with unhealthy lifestyles are less likely to attend follow up visits. If loss to follow up is associated with both obesity and cardiovascular disease risk, the study findings are most threatened by information bias, detection bias, confounding by indication, selection bias due to attrition, or ecological fallacy.
D.
So let's quickly see again. Uh, sorry. Basically, this is D, selection bias due to attrition. Then a researcher finds that crude odds ratio between exposure and disease is 2.4. After adjusting for some smoking status, the odds ratio decreased to 1.1. Which interpretation is most appropriate? Smoking is likely an effect modifier. Random error explains the difference. Smoking likely acted as confounder. Exposure misclassification is differential, or residual confounding has been eliminated.
D.
Yes, it is C. It is the classic example which I gave. Yes, it is C. Investigators studying dietary habits interview cancer patients more extensively regarding past food intake than healthy controls. Which bias is most likely introduced? Recall bias, interview bias, non response bias, healthy worker effect, or lead time bias?
B.
Yes, it is B, interviewer bias. In a study on air pollution and asthma, exposure in measurement error occurs equally among exposed and unexposed participant. What is the most likely consequence of this type of misclassification? Bias away from the null only, elimination of confounding, unpredictable overestimation of effect, or systematic exaggeration of interaction, or bias towards the null in many situations. So, yes, it is E, bias towards the null in many situations. A stratified analysis showed that the association between occupational dust exposure and chronic lung disease is 1.2 risk ratio.